All right, so let's get a few here in maybe. All right, so chapter 10. All right, so chapter 10, I only assigned a couple. We might actually do, I've been working on some in my office this morning. What number is it? Number 1. We might actually do a couple of those. If we have time. Might do them Wednesday if we don't get them today. Okay, number 1, I think what I'm going to do is kind of get you started on it, and then I might let you finish it because it's pretty easy. Okay. Well, what the heck am I doing? Oh, there we go. All right, so we calculate the torque, the magnitude direction about point O due to the force in each of these cases sketched in figure 10.1. Okay, so we've got A, and we got a little rod here, and here's point O, okay, that it was talking about. Okay. And the force applied, the line of action, is 90 degrees to the lever, so that's 90 degrees. Okay. All right. And it says in each case, playing the page, the length of the rod is 4 meters, so L, or we could say radius, or R, is 4 meters. And the force has a magnitude. The force applied is 10 newtons. Okay? All right. So I think A is pretty easy. We know that torque is equal to what? It's the force applied times the radius R, right? And yes, we can say this right here. We can say F R sine of theta. And so let's just apply it, y'all. That's easy. So we got what? A force of 10 newtons. The radius was what? 4 meters. And so what do we get? 40 Newton meters. That one's real easy. All right, what about B? All right, let's draw it again. We got the bar. Here's the point O. The force applied, however, is now at 120 degrees. All right. Well, now we got to use our sine, don't we? We got 10 newtons times 4 meters. Sine of what? 120. Okay. And that would be, and we forgot the direction, didn't we? What's that going to be? 34.6? Yeah. The torque here is 34.6 Newton meters. And by the way, let's go back up here. What direction is the torque on that first one? Notice that the rotation is going counterclockwise. It's coming up and hitting me in the chin. So the direction is what? Direction would be a dot, wouldn't it, out of the page. What about this one? All right, we're applying a force. It's going in a counterclockwise direction. Is that correct? It would also be what? Out of the page. This would be the dot. Okay, dot, dot. That's typically how you write it. So it's out of the page. All right, what about C? Okay, so we got 1C. Let's draw it again. Where's O at? It's out there on the end. All right, right there's O. All right, we got the angle is 30 degrees. All right, that's the applied force. All right. So we get what? Well, it's the torque is 10 newtons times 4 meters. Okay. Sine of 30. And what do we get? 20 Newton meters. It's real easy math. And it's also, let's see, it's also what direction? Same, out of the page. So we got direction. I'm going to put a dot and circle it. Okay, that's direction, out of the page, out of page. All right. And then we got D. All right, let's look at D. All right, let's draw it. Always draw it. There's your point of rotation. All right, and we're hitting it right here. That's a 60-degree angle. Uh-oh, and notice, too, we're backing off 2 meters. So now my radius is no longer 4 meters, it's what? 2 meters. So torque is equal to 10 newtons times 2 meters times what? Sine of what? Now we could do that a couple of different ways, but let's just keep it easy. Let's do it 60. Okay. But the rotation is what? It's clockwise, isn't it? So we get 17.3 Newton meters, right? But now wait a minute, we got clockwise rotation that way. So the torque is what? Down into the page, or it'd be negative torque, right? So we could put a negative there. All right, but it did ask for the direction, so be a little more specific. Just say that and then say out of the page. And how do we represent that? That right there. We'll do this too when we get into magnetic fields and amperage. We'll use dots and X's to represent direction. Okay. All right. And then E, 1E. All right. Okay. Let's draw it. There's your axis of rotation. Okay, the force is applied right there. That angle is 60 degrees. Okay, but now wait a minute. Notice it's applied right at the point of rotation. So what is the angle actually? Is it applied to the lever, or is it applied to the axis? Axis, so that its angle's theta is what? 0 degrees. So the torque is, I'm not even going to write it down, 0 Newton meters. I don't need to write it down because there's no torque. All right, what about F? Let's look at it. All right, so we got our point, we got our bar, it's rotating about 0.0. We apply the force that way. Okay. So the force is 10 newtons. All right. All right, now this was 0, but this is what? 180. Well, what's the sine of 180? 0. The torque is 0 Newton meters again. Okay. It's not applied to the actual length of the lever. Okay. It's applied at 180 degrees. That'd be like taking a wrench and just pushing on it, straight on it. It's not going anywhere. Bolt's not going to move. Hopefully no one's that clueless about taking bolts out. I wouldn't think you would be. All right, what about number 7? That's a good test problem there. Number 7. All right, you got a wrench. A machinist using a wrench to loosen a nut. The wrench is 25 centimeters long. All right, so we got a wrench. Let's see if I can draw this. It comes around here, something like that. Yeah, okay. Yeah, all right. There's the nut. There's the nut. Okay. And anyway, yeah, I know it looks goofy. All right. And so we got a 17 Newton force applied. All right, 17 newtons. Okay. And the distance from here to here is 25 centimeters. So R is 25 centimeters, isn't it? Now that needs to be in what? Meters, doesn't it? Because what is torque? It's Newton meters, it's not Newton centimeters. Okay? All right. Okay? All right. And this angle, I almost forgot, is 37 degrees. All right, so what's the torque? It says The wrench is done okay, and at the end of the handle at 37 degrees, now what torque does the machinist exert about the center of the nut? Okay, well, that's easy. Torque is equal to, we know it's the force through a radius sine theta, or across a radius sine theta. So torque is equal to 17 newtons, real easy. Radius is 0.25 meters, and the sine of 37 degrees. And so we should get 2.56, yeah, thank you, 2.56 Newton meters, all right? Now, and then it goes on to say, what would the maximum torque, what is the maximum torque he could exert with this force, and how should it be oriented? Okay, well, I think it's pretty obvious. Instead of pulling it this way at an angle, he needs to do what? Oh, by the way, is that positive or negative torque? It's positive torque, so the torque is going into the page. So into page. All right? It's positive. All right? Okay, so actually we need to do what? To get maximum, we need to do what? 0.25 meters sine of 90, right? 90 degrees. And what would that be? 4.25? Yeah. 4.25 Newton meters. And of course he would need to come in here and do what? The force would need to be applied right there, wouldn't it? Or right here and pulling back at a 90 degree angle. Either way. Right? Yeah. It'd be kind of hard to pull on a wrench like that, but I guess you could. Okay. Remember adding a cheater. Why does the cheater help? Well, it increases the lever arm length, so you don't have to use as much force. Okay. Put a cheater on there. What? Yeah. You put the cheater on there, and you don't have to push as hard, right? Well, in a practical, if it's been there a long time, yeah, you're probably going to cut that one off, yeah, or twist it off, yeah. Or use a torch. I have used torches and heated them up. That'll help too. You might heat it up with a torch and then loosen it. Yeah, that'll work. But sometimes you twist them off. You just, especially if if it's got Loctite or something like that on it, yeah, you probably